Another lovely day of team. Welcome everybody. Today we have Martha White going to tell us about improving regression performance with distributed losses. Welcome, Martha.
Thanks, Rich. You don't have to talk. Okay, so this is a tea time talk. You guys can interrupt me at any time, but just like Rich on Monday, I made it too long, so I'm going to try to go through a little bit more quickly, but still feel free, like you can interrupt me. There are at least a few more seats, like one here and two over there, if anyone's willing to push up. Okay, so I'm just going to start off by telling you what you're going to get from this talk, and then I'll kind of go through the story of the talk and how we try to identify that distributional losses are useful for regression. So maybe you've heard of distributional RL, and there's been some nice successes there, and in classification as well. And so what we did is went and looked at this in the regression setting, which is more simple than the reinforcement learning setting. And these are sort of the conclusions we have so far. I would say very preliminary conclusions. This is a hard question. But the first takeaway that you'll get from this talk is that distributional losses, which maybe you don't know what that is yet, but you'll know soon, distributional losses improve prediction accuracy in regression. So they never really seem to harm performance, as opposed to, say, using a standard squared error, and in some cases really improve performance. We have some hypotheses why, and we kind of try to narrow down into what we think is maybe one of the most promising hypotheses, which is that this loss is just better behaved, and so it seems easier to train, and that gives us better performance. Okay, and the last takeaway we'll take from this is that we propose a particular distributional loss, which we're currently calling the histogram loss. I'm going to ask for your feedback on that. And this loss is really easy to compute, so it's both more effective and easy to compute, and we're kind of proposing that maybe it's a good replacement in regression when you go into TensorFlow or you go wherever you're going to pick your loss, then you might just choose the histogram loss instead of the least squares loss. Okay, so that's kind of where this story is going to go. And let me just tell you why we even care about distributional losses. So why do we start off by asking this question about changing the loss to a distributional loss? Okay, so in classification, there's all these really nice results. So you can take your outputs, your labels, and you can change them a little bit. So we're going to modify our outputs either by adding noise or by somehow incorporating extra information, and this seems to improve performance. So for example, label smoothing just takes your hard 0-1 labels and gives some amount of probability to the other labels, epsilon probability to the other labels, and just removes that epsilon value for the label that is actually the true label. And this seems to improve performance. Label ambiguity is this really nice paper recently, 2017, that tries to incorporate some extra information about other labels that are plausible, not just uniformly randomly giving extra epsilon, but saying, this group of classes for this instance probably have some possibility of being active. So it takes a little bit more expert information, but again kind of smooths the outputs a little bit. And this is sort of related in distillation as well, where instead of learning hard 0-1 classes, you're given probabilities by a teacher or an expert, and again that seems to improve performance. So in classification, there's kind of a compelling story now about changing these outputs improves prediction performance. Okay, in RL, there's maybe a little less exploration, but also some pretty exciting results, and a little closer to the regression setting, because we're often doing something like regression when we learn value functions. Okay, so in reinforced learning, the idea was to learn a distribution over returns rather than learning the expected return. And then in control, even though you learn this distribution over the returns, you would still just take the mean of that return, and you'd act according to the expected value of the return anyway. So surprisingly enough, this approach improved performance in lots of tasks. And a natural question that arose after that is, why would that help improve performance? Why would it help to learn a distribution and take its mean, which is just a lot more effort, rather than just directly learning the mean? Okay, so sort of I put should not improve because it doesn't seem like it should have any improvements. Okay, but it does. So the natural question is, what is going on? And that original paper and the classification paper sort of give some nice hypotheses, I think, about what could be giving this improvement. So there was sort of this multitask learning hypothesis. You're not just predicting one thing now, you're predicting many things. And we think predicting many things can be good. Although this is in itself something that's sort of still being explored. But there's some idea that could help you improve your representation. Another idea is that if you take your outputs and you add a little bit of noise to them, that can be good in terms of generalization. So you're not going to fit as strongly to your targets, and so this label noise could be a good thing. and kind of moving from an expected value to distribution maybe adds some similar noise. There's an inductive bias idea that maybe you can actually inject some knowledge into your problem by changing the outputs. And I like this one the best, a stable incremental learning. So whenever you do an update on every time step, you're modifying a smaller number of weights with a less large magnitude value. Okay, so in this talk or in this work, we went through and kind of tried to identify some of these properties. We couldn't really go through all of them. But in the end, what we're going to explore more as a hypothesis is that it's a well-behaved optimization problem. Go ahead.
Quick question. Could you clarify that last thing you said? Like, why is it that you're updating the weights less?
Say that again?
Like the last thing you said, that you're updating the weights less?
So it is hard to explain exactly this without me telling you what I mean. But let's imagine you have a vector of values that you're producing, which is the probabilities, like a distribution. But let's say they're probabilities of being in different classes. Whenever you update your weights with, let's say, when you see some classes, only a small number are going to have, say, higher probability, and the rest of them are all going to be 0. So first of all, you're only updating a smaller number of weights in a larger magnitude way. And since you're spreading this all out over bins, this is too hard to explain. Let me show you when I get to the bound that we have on the gradients. Okay. Okay, so that's kind of the questions we'd like to go through. And now I'm just going to tell you what is the regression problem, what does the distributional loss look like, and then I'm just going to kind of dive into some of the experiments where we tried to go through and check, was it the multitask hypothesis, and so on. Okay, again, interrupt me if I'm going too quickly or if you're confused. Okay, regression. Everyone knows what regression is. Our goal is going to be to find some function f so that, for example, according to the squared error, we can predict some target label y. And I'm just going to assume it's scalar. We could, of course, have a vector of values, but it's perfectly fine to start with scalar. And for the squared error, our solution f of x is typically approximating expected value of y given x. If our function class is sufficiently powerful, then this approximately equals is actually equal. And then, of course, in regression, we could consider other losses, like the L1 loss. Instead of a squared here, we could do absolute value. And then we're predicting now instead the median of y given x. But in general, let's just think about it as we're predicting something like expected value of y given x, and I'll focus a bit more on squared error. Okay, so there are all these other losses. Regression has been around for a long time. There are many, many losses out there. So these are kind of the things that have been explored, mostly robust losses. Here now we could predict instead the entire distribution, probability of y given x, and then take the mean, which I've kind of already told you why would you do that. But let's do it anyway. So this is the alternative typically considered. We're going to do this sort of weirder alternative for regression that hasn't really been considered other than in the distributional RL case. And I'm just going to remind you that oh, go ahead, Martha.
Sorry, Martha, what do you mean by robust losses? What does that mean?
What are robust losses?
Yeah.
There's this whole literature about if you would like to learn this function f, you want to make sure that your learning is robust to, say, outliers. So this squared error, if you have some y that is, say, shooting off somewhere, then you're going to focus really strongly on that y. So robust losses try to be robust to things like that. But there's lots of different types of robust losses and robustness to different types of problems you could have in your data. Okay, yeah, so like I said, let's do this anyway, but I just want to remind you that my goal, though we're going to learn the distribution probability of y given x, my goal is still to predict expected value of y given x. We don't really care about learning this distribution, we're just doing it anyway. And this sort of differs from classification and distributional RL because in classification we really do want the distribution of y given x. That is exactly what multi-class classification is trying to do. We learn a vector of probability of y given x, which is the probability of being in each class. And technically the distributional RL paper was all about trying to learn the distribution of returns, even though they didn't end up using that in the end. Okay, so we're going to incorporate this distribution and the loss to define something with useful properties. I'm going way too slow. Okay, I'm going to speed up a little bit. It's already been 10 minutes? Okay. Okay, so I'm going to tell you what this loss is going to look like. So first, let's assume we have the distribution over y, which is conditional on x. So imagine that you just had access to this true distribution, and we're going to learn some parameterized q of x to approximate probability of y given x. Okay, so we're going to do what is typically done. We'll take the KL divergence between these two distributions, and we'd like to find q of x so that it is as close to p as possible, the true distribution over y. Okay, so this KL divergence includes this cross-entropy term It includes this differential entropy term. We can ignore this because we only care about Q of x, so this has no influence on our objective when we minimize over the parameters in Qx. And so really we just have to focus on how are we going to minimize this cross-entropy term. Okay, and so I mean, when you're looking at this, in classification this isn't as difficult because we just sum over all possible y. Let's say you have 10 classes, you just sum over your 10 values of y. But here we have to integrate over all possible y, and this isn't always going to be easy to compute. So this thing could be expensive to compute. Okay, so once we start thinking about doing distributional losses in regression, we're going to have to change it. We're going to have to restrict ourselves a little bit so that it's going to be feasible. So in our setting, we're going to restrict this Q of x to be a histogram density. And by that I mean, actually I'll just show you what the picture looks like. By that I mean Q of x is going to look like this. You're going to say, what is the probability I'm in each of these bins? But to be more precise, I'll just tell you what I mean by that. So we imagine we have some support A from A to B, that is where our true values y are going to be in. And now we're going to learn some function f of x so that the first entry tells you what's the probability y is in bin 1, all the way up to what's the probability y is in bin k, and you have k bins, like we have in a histogram. Okay, and the density now is just defined by the probability you're in that bin and divided by the width of that bin. And now we integrate over that entire density, you're going to have a valid density function. Okay, so here, for example, we have 30 bins, and the width of these bins is uniform at 0.25. And so this sort of tells you what you think the distribution over y is. And here I'm always subscripting with x to make it clear that we're not actually learning the distribution over y. It's always distribution of y given x, but it's kind of confusing to write condition on x here. This is just a function of y right now. Okay. Okay, so we're going to restrict ourselves to this form. This is a pretty particular density, but now if we pick that form, the histogram loss is going to be easy to compute. So this is the loss that we're going to be proposing. So this is the loss. It has changed from this integral to now being this fi of x is the function we're going to be learning. So that was the probability of being in each of those bins. Okay, and we had an f1 all the way to fk, and this pi is just some coefficient, some constant coefficient. And I'll just tell you what the pi is. So if we just look at how the cross-entropy simplifies when we pick this density on Qx. So if Qx has to have this histogram density form, then we look at this term. It simplifies by just plugging this in, and the sum can come out to the outside. Okay. Now that the sum is on the outside, we have this term right here, and I'm actually not going to go through all these steps. But when we integrate out over this term, if you'll notice that this doesn't have anything to do with the y, so it's going to come out, and we're just going to get this difference between CDFs. And because this is sort of actually pretty intuitive, what it's hard to look at, it's really just saying I have all these bins covering this space. This is the edge of one bin, and this is the edge of another bin. And this coefficient is just telling you how much did the probability increase. So how much did the CDF increase when I went over to the next bin. So it's just this little line right here. Okay, so you're just looking at your CDF over time and just grabbing these little differences that are the coefficients. Okay. Okay, so in order to actually get this loss, you just have to go through your data set. You have to compute all these PIs for your samples, which I will tell you how we're actually going to compute those PIs, and then we would have our loss. But I see a hand. Go ahead.
I wonder if one of the bins is empty, then the P would be 0. Is there any way to limit the Q so that it's not, because it basically doesn't matter what Q is.
It's a great question. I will say it's actually not about Q. This is not the CDF for Q. It's actually the CDF for P, the original distribution that I was talking about. So like this true distribution, which there's no point in going all the way back here. Let me just draw it on here, for example. Nope, I don't. Okay, so for example, here, it's the CDF for this true distribution. So if your true distribution over y is Gaussian, then that f is the CDF for that Gaussian. It's not the CDF for the histogram, if that answers your question.
So that requires that the true distribution doesn't have any entity. So it's either a Gaussian or something.
Okay, right. I see what you're saying. So you're saying if we were to go look at this cross-entropy term, whenever we're looking at this probability of y.
Yeah, so if the P of y is 0, then it doesn't matter what Q is. So it given like very high prediction, that will.
And that was just really the property of the KL divergence when you have this ordering on these variables this way. So yes, you're right. I'm not sure it's a problem though. Okay. Okay, so I'm going to give you an example. But before I give you an example of what this loss looks like, I just want to mention a few reasons why I think this is sort of an important restriction and why this is useful, or why this loss is useful. First, it's convex in the parameters that we're going to care about, so it's convex in this Fi. It is efficient to compute as long as you can compute this CDF for the true probabilities P, and it's pretty interpretable actually. So we started off by saying, I'm going to learn some Q of X that matches a P, and I'm going to minimize the KL divergence. And in the end, you have something that looks a whole lot like the cross-entropy. So really, it's sort of like a cross-entropy term where the choice of the true distribution, so the true distribution over Y, is really just going to change these coefficients Pi. So the choice of your distribution is just going to upweight or downweight how important each of these bins really is. So it sort of has some interpretableness there. Okay, anyway, let me show you a more concrete example of what this loss would look like then. So I haven't really told you where this true distribution comes from, so maybe it's a little hard to imagine how we would compute this loss. Okay, so we are the designers of this loss. Actually, we're going to have to make up what the true distribution is. We are not given a true distribution. The Y's that we are given are just samples. So we're going to do sort of like you do in label smoothing. We're just going to pretend there's some distribution and the one that we picked is okay. So we're going to, for example, pick a truncated Gaussian that says we believe that for a given x, this y is distributed according to a Gaussian distribution with some variance sigma squared, and the mean is actually the sample that you saw. So for sample xj, yj, we're going to pretend the distribution over y given x is this truncated Gaussian, which is absolutely definitely may not be true. Like, it's just something we are imposing on our problem. Okay, but if you make this assumption, it's not difficult to compute these PIs, as ugly as this thing looks. You guys are used to this CDF function for a Gaussian, so that's not so difficult to compute. And so we would just go offline for every point in our data set. We are now defining an xj and its corresponding distribution over yj, not just yj itself. We'll compute all the PIs for each of these bins that we're going to have, and now we are going to have our loss. Okay, and then when we actually go and learn, we're going to learn an Fi that is a softmax function that just tells you what's the probability I'm in each of these bins, and the parameters you have to learn are the W's and the thetas. Theta here just represents, say, a neural network. That's going to produce your last layer, and then you're going to linearly weight those with some weights. Okay. Everyone following? Good. Okay, and in general, you can go and actually define lots of different losses if you just decide, I don't think that a truncated Gaussian is a good choice. You know, I could put a mixture model in there or other types of distributions if I thought that was useful. We found in all our experiments that a truncated Gaussian was fine because we are sort of just using it to try to improve performance in a strange way. Okay, one question I sort of anticipate is how is this different from cross-entropy for classification? Because really it just looks a whole lot like cross-entropy. So it does look like cross-entropy, but I just want to remind you that we are doing regression. So the similarity between these two things is just because we chose Qx to be this histogram density. If Qx was some other density, then our cross-entropy term wouldn't have looked like the cross-entropy for classification. Okay, and then even in this setting where we did make this choice, the difference now is still in how the weights Pi are specified. So for example, multi-class classification where we use the cross-entropy, the PIs are all 0, except for one of the PIs is going to be 1. Go ahead.
Would you say that's the exact difference between the original dist RL paper?
Would you, sorry, say that again?
Like the distributional RL. I'm trying to figure out how this loss is different from the original one proposed in distributional. And that third point, that third bullet point is that the answer, right?
In fact, I would say it's this answer. The PI in the HL determined by the target distribution. And in the original distributional RL paper, actually they look at the difference between what you think the return is when you do this like projection, like you apply your Bellman operator, and then you look at what you thought the return was. And so actually the only difference is that we can pick whatever we want for this target distribution, like, you know, nice Gaussian mixture model, whatever. It's easy to compute. But in say Mark's paper, they sort of wanted to keep the two forms the same. So they made both of them be categorical. What they called categorical distributions, we decided to call them histogram distributions because categorical distributions are usually for discrete random variables. And we just want to make sure everyone remembers that we are doing regression. So that's, but what they would have called categorical, we are calling histogram.
But like specifically in the loss, you get this PI term because of how you're choosing this, I don't know what to call it, but the target distribution or this functional form of the
QX.
Yes.
And when I'm saying target distribution here, I mean actually the true distribution that we've made up, the true target distribution probability of y given x, which may be anything. It could be other distributions. It doesn't have to be this categorical thing.
Right. So you can argue, I don't want to take up time, but you can argue that if you choose the right distribution, these PIs are basically going to help. If you choose the wrong distribution, these PIs that you're weighting your loss by are going to hurt.
You would think so. Right. And in fact, for some of the cases, we can choose PIs that are, for example, very aggressive, like multi-class classification, where you say, I believe Y absolutely has to be in this bin, and it's not allowed to be in any of the other bins, and we're calling that HL1 bin, and it does really badly. So it's not like choosing any distribution will work. The smoothness seems to matter, and something seems to matter. Okay. Okay. So we'll just give one, I guess, hypothesis about one, I guess, piece of evidence theoretically why we feel like it should be the optimization properties of this histogram loss, and then I'm gonna go through some experiments, which I still have. Okay, good. A good 4 minutes. So I'm just going to summarize this quickly. There's this really nice work that I think is called Train Faster, Generalize Better, that says if you get that the generalization performance of your method is dependent on how quickly you can train. So if you can converge faster on your training data, that's good. And if you have good Lipschitz constants for your loss function, so that just means if the norm of your gradient is well bounded, these two things both really determine how well you generalize. Okay, so what we'd really like to have then is that our gradients are well behaved. I'm just going to summarize this quickly because I don't have that much time. But the idea sort of is that we compare these two components. So here in the HL-Gaussian, where we assume this truncated, we get this histogram loss. This term is the difference between the true probability value and what you predicted the probability was for that bin. So this number is never going to be greater than 1. And the same term that's in the squared error, for example, is f of x minus y. So this number could actually be quite a bit larger if you just, you predicted, your f of x could predict lots of different things. It's not guaranteed to be between 0 and 1. So even just looking a little bit about how the gradients of their norms are bounded could suggest that this one is going to have better, is going to be able to train better than the squared error. And the same is true if you consider other things not like the Gaussian. If you consider this hard 0, 1, it also doesn't have as nice gradient norm properties. Okay, because I'm running out of time, I'm going to jump now finally to this question. Okay, I've told you how we can define distributional losses for regression. I've told you a restricted form so that it's actually computationally feasible and we can actually explore it properly. And now we should ask the question, does it actually improve regression performance? And I've sort of already revealed that it does. And if it does improve regression performance, why is that? Okay, so we conducted some experiments on 3 data sets, and we sort of dove into one data set where there seemed to be more difference to try to understand what was causing that difference. So we used this CT position data set more, which had 385 features, 50K samples. We picked this network architecture, so 385 inputs in, and then 4 layers of 192. This was chosen to make the squared error loss do as well as possible across a bunch of different network architectures that Hassan tried. And we fixed the number of bins used in the Gaussian and fixed how the variance is set. And for regression, we normalized the targets because that was really important for getting regression to work well. Okay, good. Okay, now I'm going to dive into results. So the first thing was, does this help? Okay, we reported lots of stuff in this paper to try to give a more complete picture of what was going on, but I'm just going to highlight in boxes the thing that you should look at in this table that's going to have way too many things in it. Okay, so the first thing you're going to notice for this data set is that linear regression is just a baseline, meaning no neural network whatsoever, which does really, really badly. But it's just there for comparison. Regression means that neural network using a least squares loss, or the squared error, and HL-Gaussian is using that HL-Gaussian loss. So the difference between these two things is really stark. Almost double performance improvement, which is a lot. And we'll try, there's going to be a bunch of other methods here, and they're not going to get nearly as close as this much improvement. And I'll mention that for the other 2 data sets, the gap is not as big as this, but it was still statistically significantly better. So kind of the story is it never harms performance and sometimes really improves performance. Okay, so it does help improve performance. And now why is there this improvement? So I gave you these hypotheses that other people had given. We sort of explored these ones a little bit more specifically. So one thing you might think is learning a distribution is harder in some way. It's kind of like this multitask hypothesis. So maybe it gives a better representation. Maybe adding label noise is actually what's causing this to improve. So if we just had added label noise, that would have been enough. And the other thing is, of course, we had this loss where we got to tune a bunch of knobs. Like we have all these bins, we have variances. So maybe this is giving us a chance to kind of balance the bias-variance trade-off. Okay, I'm sort of going to step through these and say how none of them are really seem to be the effect. Okay, so learning other distributions does not seem to be effective. So here, I'm now revealing all the other lines in this graph. So MDN is mixture density network. Mixture density networks, that's this box right here. So you can see it actually improves performance a little bit, but it didn't make the significant jump that we saw from using this distributional loss. Again, a mixture density network is learning a mixture model on the last layer. It's actually trying to truly model probability of y given x using a more complex distribution. And we swept over all these values and picked the best one, and that's how well that did. Okay. Oh, but still, for the mixture density network, we learned the distribution, we took the mean afterwards. Okay, so that seems to be one conclusion, is at least using mixture density networks didn't seem to give the same effect. I guess this is maybe a somewhat strong statement. Maybe learning other distributions would have been effective, but in this case, this was not effective. Okay, adding label noise also doesn't seem to be as effective. So here we tried this algorithm, which I'm calling regression noise, and another one called label smoothing. Regression noise, we just took the targets and we added some Gaussian noise to them. Again, sweeping over a bunch of different noise parameters and reporting the best. And label smoothing, sort of like the thing where you added some epsilon to the other classes and then reduced the epsilon for the main class. With some probability epsilon, we chose a random value in the range A to B, a uniform random value, and otherwise use the actual target. Okay, so that one doesn't help at all. In fact, it harms performance. And adding a bit of noise does seem to help, but still not to the same level. Okay. This is a little bit more complicated to explain. So since I'm sort of running out of time, let me just give you the high-level conclusion here. There's these things we can change, i.e. the number of bins and how wide or narrow we make this sigma in our truncated Gaussian. And you would think we could very nicely, narrowly fiddle with that to get this really good performance. And we're just cheating by fiddling with that. But actually, these lines are sort of saying that even in a pretty broad range, this doesn't really seem to be giving this ability to cheat in this way, and there doesn't seem to be a really clear bias-variance trade-off either. So what would a bias-variance trade-off look like? Look at the blue and the red lines. Blue and the red lines, mean absolute errors on the y-axis. We would expect at some point the training error to go down and the testing error to start going up, but they mostly seem to parallel each other. And for a pretty broad range, this is a large variance value right here, it still does better than regression. Okay, so that's sort of the takeaway there. We could, actually, this was our first hypothesis, that we were getting some bias variance. We tried really hard to figure out what was going on here, but it doesn't seem to really have a clear bias variance trade-off. Okay, and then the last experiment I'm going to show you that is saying is not, something is not the reason, is trying to look at the representation. So the last thing we did was take the representation from each of the two different solutions and swap them and see maybe the histogram loss learned a good representation. It did a much better job of solving the problem. So if it actually caused us to learn a better representation, that representation should be useful for the the squared error learner as well, if that makes sense. If you actually imagine that this learning a distribution was giving you a better representation. Okay, so that also doesn't seem to be true. Here, fixed means we took the representation from the other learner and just fixed it on the last layer of the neural network, and then just retrained the weights on the last layer. Okay, so the important one to look at is regression was doing pretty reasonably well, and then you swapped in this new representation, and it makes things way worse. It doesn't make things better. So the conclusion there is the representation isn't some generally better or more useful thing. Okay, then we tried several other things, but I'm sort of running out of time, so I'm going to not tell you.
Did you retrain the last layer on that fixed?
Yeah, exactly. We gave it the representation and let it retrain. And then we also tried just initializing with that representation, maybe hoping it would bring you to a better part of the space, and then let it train the whole thing again, and that didn't help either. And we even tried with a random representation. It seems to improve performance over that too. It's sort of weird. Okay, so the last thing I'll conclude with is then we also tried to look a little bit about its performance as it's learning, and we kind of wanted to look at two things. What does the norm of the gradient look like? and what does the learning curve actually look like as it's coming down over epochs. Okay, so this yellow line is the HL-Gaussian. HL1 bin is that really harsh distribution I mentioned to Mark about you put all of your magnitude has to be in one bin and you can't have any values in the other bins. That just generally did badly across all of our experiments, but it's just here for comparison. So one thing you'll notice is that it trains down much faster, and correspondingly it's, right. So this one right here, this trains down much faster, and you'll see if I had the testing curve here, which I thought I included, but I don't. It also comes down nicer in terms of testing as well. And here, this is the gradients of the norm of the gradients, but normalized by their median value. Okay, so there's kind of two things to notice here. The regression, which is blue, is much, much noisier compared to its median. And the green line and the HL1 bin, they look like they're sort of similar, but that's only because the median of this HL1 bin is really large, so it's making it look like the two things are really similar. So this, if we were to really compare these two things fairly, which we might change now, the yellow one you would see being a much broader range. So it seems like the gradient of this yellow line is much better behaved, and that's the best hypothesis that we have for why this is actually doing better, since it doesn't really seem to be the other ones. Okay, so I'll leave this off with some discussion questions. We tried to kind of go through and systematically check, is this the reason that our histogram loss is doing better? So actually start off with Hassan going off and noticing that it gives a much better performance, and then we kind of just stepped through and tried to see, well, is it this reason? Is it this reason? And our conclusion kept seeming to be, no, it's not any of those reasons, except for that it seemed easier to train. But one question we have is, are there other confounding factors that we're not really noticing? Like maybe in some of these experiments there was actually something else. Maybe it was a representation and we didn't really notice. So I think that this is an important question for these experiments. I think that the loss is a little different than what's used in distributional RL, so you could ask the question if it would help performance there. What do you think of this name, histogram loss? Something we haven't actually answered is, what is the bias of this loss? Is it consistent? I think the answer is no. And when I say consistent, I mean, is the true solution actually going to give me expected value of y given x? And of course, the last question is just a super open-ended question. What does it mean to learn a good representation? If we had a better answer to that question, maybe we could actually check, did our method learn a better representation that we could and actually answer that question? Okay, thanks. It took way too long, but we still have a good 3 minutes for you guys to ask questions. Oh, Janie has a question.
I just wanted to comment that at least the first distributional IL papers found from these groups in 2010. It is very well motivated because they want to solve this sensitive problem. So that's why they need the distribution of the returns instead of calculating the mean.
Totally agree. So the part here was to say, why does it then help to then take the expected value rather than using, of course, learning distributions is just a useful thing to do. But our goal is not to learn the distribution for any useful purpose other than what seems to be good for getting the expected value. Go ahead, Roshan.
So did you look at the shapes of the histograms that they learn? Do they look like normal distributions, or are they like multimodal? Or
We did look at the shapes. I'm going to ask Hassan though. Hassan, what do the shapes of the histograms look like?
They're mostly not like maybe bombs or so.
Right, and the target distribution was unimodal as well. So that sort of makes sense.
And the reason I wanted to ask that is because so if your class of distributions instead of being a histogram becomes just a Gaussian distribution, then that just gives you squared loss again, right?
Okay.
Because the Ki divergence is this squared difference in the means. So I was wondering, so this seems like a clever way of introducing nonlinearity into the problem.
Right.
Because if your target model was linear function plus Gaussian noise, but here it can be linear function plus some distribution that you're learning. So
right.
in effect, it becomes like a nonlinear. You're turning regression into classification by splitting up all the regions into bins.
Right.
So maybe, yeah, like the power of the model seems good. Like it's an interesting extension.
I agree. We had at first we sort of actually thought of it that way, that we were reducing it to, or changing it to a classification problem, and this loss sort of seems like it introduced this nonlinear layer. We still don't know exactly how to reconcile that with just thinking of it as a loss where you're trying to match two distributions. It could be a useful way to think about it, I agree. Go ahead, Mohammed.
So the target distribution is a Gaussian, right?
Yes.
So why can't you just plug in the predicted distribution as a Gaussian as well and just predict the mean and standard deviation?
This is sort of what Roshan was just saying. The answer to your question is, I suppose we could have done that. It would have been, it'd be one of many of these. It wouldn't be histogram loss, but it would be part of this class of KL divergence losses where you said, I'm going to take my target, I'm going to change the distribution, and now I'm going to minimize the KL divergence. So the answer is we could do that. I don't think it's going to do particularly well, but we should probably try it.
Why wouldn't you do it?
Sort of for the reason that I think that the properties of this loss are going to be particularly good because we are doing this thing of binning up the probabilities into your probability in bin 1 and bin 2 and so on.
So it's not about learning the distribution, but about the sort of distribution you're trying to learn?
Again, a good question. So actually the real way that this came about is we started from the other direction. We thought, well, all these categorical distributions are doing well. And then later we came to this view that really we can just think of this like a KL divergence where we've restricted the form of our probability model to be of this particular form. And it seems like a more elegant way to think about it. So the answer to your question is really, it's because we started with this distribution and we continued with that distribution because it does well. But other distributions could also have nice properties and we don't really know yet.
Have you tried Gaussian?
I'm going to look at you, Hassan.
What do you mean by like minimizing a KL divergence between the Gaussian and the Gaussian targets?
Yep.
And also learning like means and variances.
That is the
But
squared loss.
yeah, it would be the square loss. But then if we were also learning the variance, we have to add in the fact we have to learn the variance as well.
But then I was reading a paper where if you explicitly do that, it allows you to attenuate your loss.
Mm-hmm.
So that if you have a noisy label, you can predict a high variance and get away with it.
Isn't it like the Gaussian noise?
Except for in that case, it would still be a fixed variance. So it is true that we might not learn the variance parameter here. This is probably taking too long, but we should talk about it offline. Maybe we have to end here now, actually, and then other people can ask me questions. Yeah, I think we probably have to let everyone go. Thanks, guys.